Ladies and gentlemen, I'm Professor Ville Vuorinen from Aalto University in Finland, and I will give this talk about lessons learned in OpenFOAM large-eddy simulations on sprays and flames in the past 15 years. And I would like to acknowledge my co-authors and collaborators, PhD students and postdocs in the past who have contributed to the work on reactive flows that I will be talking about. First, background. So you have to start somewhere when you start research. And I personally completed my PhD in 2010. And at that time, I was the first OpenFOAM based PhD thesis in Finland on LES of particle-laden jets and Stokes number effects in fuel sprays. So our group at that point had a long history in studying fuel sprays. You see a shadow graph visualization of a diesel fuel spray here in the bottom. And the puzzling question had been that what is actually happening over there, and how do we simulate the multiscale phenomena in such sprays? So I started my PhD and I studied particle-laden jets, air jets with small particles, and here you see the droplet timescale and the Stokes number, and basically what I was studying is that how does the particle size and the Stokes number affect the dispersion patterns of the spray particles. And as you can see, the smaller particles are more dispersed in sprays than the large particles which have more, let's say, ballistic trajectories, and they are less sensitive to the turbulent flow. So that's where my academic career kind of started from. After that, I became a postdoc, and our main OpenFOAM research goals in 2010 and 2014, in those 4 years, was roughly the following. We had two goals. First of all, we wanted to implement non-reactive density-based Runge-Kutta 4 large-eddy simulation solver into OpenFOAM. And the other goal was to implement reactive flow LES solver for diesel sprays. And that was actually the ECN, Engine Combustion Network Spray A target case that we started investigating. And here on the left, you see some of the research I was working on during my postdoc on large-eddy simulation of highly underexpanded gas jets, so supersonic flow, and we also did some experiments by Ville at that time. And this resulted in a couple of publications. And on the other hand, on the right, you see illustration by my former PhD student Heikki Kahila, and we studied large-eddy simulation flamelet-generated manifolds, FGM, of diesel flame in those years. And so this is a non-premixed combustion problem where you have a lifted flame, and application could be any diesel engine or a marine engine as well. In 2014, I became assistant professor, and in those years, it was somewhere between 2013 and 2014, we understood that in marine engines, diesel spray assisted compression ignition of premixed natural gas is scientifically poorly understood. So diesel spray has a high reactivity. You can ignite it by compression very easily, and natural gas has a low reactivity, so it doesn't ignite by compression easily. So we stated further goals, and the goal 3 was to understand dual fuel ignition, and goal 4 was to understand flame establishment. So how does the ignition develop into a flame. And in this visualization from 2021, our recent results, we have been studying the dual fuel spray assisted ignition of low reactivity fuels. So you see a high reactivity fuel spray and development of intermediate radicals, and eventually you see ignition typically in the spray tip. And now the question here is that what is the difference between ignition and a flame? So the question was, how can we simulate the dual fuel problem? That was the question already 10 years ago. And the first problem was that the FGM development for dual fuel is difficult to implement. You need to understand the problem very in depth, and it didn't seem to be a straightforward approach to us at that point. And the other problem is that simulation of premixed flame establishment is extremely difficult. And this is mostly because of the large scale separation between the spray scales and the flame thickness. So our solution was that we developed DLB-FOAM, which is a finite rate chemistry code with dynamic load balancing in order to accelerate the chemistry. And DLB-FOAM utilizes analytical Jacobian evaluation via the PyJack routines. And here are the links to PyJack and DLB-FOAM, our DLB-FOAM GitHub repository. And I am not going deep into the details of DLB-FOAM here, but if you haven't seen it, please check my talk on DLB-FOAM at the OpenFOAM combustion simulation seminar series last autumn, where I explain further details based on these two publications, and that presentation also includes 4 tutorials, links to 4 tutorials on YouTube how to use DLB-FOAM. Now I'm going to part 2, and I will talk about spray-assisted ignition of dual-fuel and tri-fuel mixtures. There is a bunch of papers where the DLB-FOAM has been used already to study this type of problems. And let's talk about the dual-fuel pilot ignition problem a little bit more. So what is dual-fuel pilot ignition? So you want to ignite premixed methane, low reactivity fuel by a diesel spray, the high reactivity fuel. And here you see a sequence, 3 time snapshots from a diesel spray evolution. So in the step 1, you inject the diesel, you have turbulent mixing, and the droplets vaporize, and eventually the chemical reactions start. And in step 2, the diesel ignites. You have these small ignition kernels. You have them typically in the tip of the spray, because that fuel has had the most time to chemically evolve. And then finally, in step 3, the methane ignites. In the ambient around the spray, we have premixed methane air mixture. So this is the dual fuel pilot ignition, spray assisted ignition problem. So now let's take a small theoretical glimpse into what is the issue here. So how does ignition differ from a flame? So how does ignition transition into a flame for stratified mixtures? So as background, this is a question about the relative dominance of deflagration versus ignition. So this has been known for the past 20 years or even more. But basically you have a laminar flame speed SL and the ignition wave speed Sign, and Sign is defined as inverse of the gradient of the ignition delay time over here. And we extended this work via an analytical formulation for combustion mode characterization in dual fuel mixtures, and this was published a couple of years ago in Combustion and Flame. And so the question is that if you have a stratified mixture, if you look at the small picture in the bottom right, you have first ignition points in the stratified mixture, and the most reactive fuel ignites. And now, is this an ignition wave or is it a premixed flame? And we shed some light with the extension of the Sankaran theory into this problem. But if we go more to the topic of the talk and the spray context, last year we decided that let's study a simplified spray problem, because DNS of sprays is rather challenging and computationally unfeasible. So we decided to carry out a DNS study of 3D dual fuel shear layers where diesel stream ignites lean ambient methane. So what we see over here is 5 different Reynolds numbers. Reynolds number 0, no convection, then increasing Reynolds number, we are always doubling it until Reynolds number 1500. And you see that in the shear layer you have n-dodecane, and in the ambient you have the blue is lean methane. And you see how the ignition starts from the most reactive part of the shear layer, and depending on the amount of convection, you see the vortices evolving, and higher the Reynolds number, you see more turbulence. And now clearly you see that okay, there is mixing, turbulent mixing, but the question is still that even though it ignites, so is this a flame or is this just ignition that we are looking at? And we did budget analysis on this problem, and actually this budget analysis indicates the first numerical evidence on premixed flame formation in a time scale of roughly 0.2 to 0.4 ignition delay times. And ignition delay time is defined based on the most reactive mixture fraction. And here you see 3 different Reynolds numbers, 375, 750, and 1500. And we look at the budget balance of the diffusion and reaction terms. And this balance indicates that there is something resembling a premixed flame deflagration occurring in this kind of shear-driven problems. And the flame structures for different Reynolds number seem to be somewhere between or close to 1D single fuel and dual fuel premixed flames on the studied timescales. And here we are looking at different Reynolds numbers again and comparing the simulation data, the 3D points, the scatter data as a function of the methane-based progress variable. And you see that indeed the 3D data is somewhere between these 1D predictions. So indication again about the flame structure, and the y-axis is the normalized CH3 species. Now we wanted to go further into the spray direction, and what we decided is that since DNS of a spray is very challenging, we decided to carry out embedded DNS of dual fuel spray assisted ignition. So this is work under review presently, unpublished work, but what we did was that we did embedded quasi-DNS, and what it means is that we had a locally highly refined simulations on a background LES grid of spray-assisted methane combustion and flame initiation. So basically what we do is that we first of all simulate on an LES grid the vaporization and mixing on a 62 micrometer grid, and then we spot out where is the ignition going to take place. And we see it over here, and in this region we draw a smaller box, and this is the quasi-DNS zone where we have 4 refinement levels to resolve the flame. And in these e-DNS simulations, we study the ignition kernel development, and we have 10 grid points per flame thickness to actually solve the potentially appearing premixed flame. And here in the bottom part, you see how the flame kernel is growing. But this is still a question that is this ignition or is it the premixed flame? And as a remark, these are really massively parallel simulations on a supercomputer requiring very, very large data storage space as well, 50 terabytes or so. And as a preliminary result of this work under review, we presented and found first numerical evidence on spray ignition kernel developing into deflagration front in a timescale of 0.3 to 0.4 IDTs. And this is a timescale which is consistent with the 3D shear layer investigations. And indeed, this is what was shown in many ways in our preprint, but the energy budget analysis in particular across thin zones between the burned and the unburned regions indicates that there is a balance between reaction and diffusion, which indicates the premixed flame formation. Finally, I'm going to premix turbulent flames and just going to give you some examples on published and work in progress. So we have used DLB form for DNS of turbulent premixed flames and flame wall interaction. This is work by my postdoc, Parsa Tamadonfar. And on the left, you see simulation of 3D turbulent premixed ammonia air and methane air flames. Lewis number is 1, and this was work published in Flow Turbulence and Combustion last year. And then in the middle, we investigated by DLB form as well, 3D ammonia air flames enriched with hydrogen. And now we used mixture averaged transport properties. And this work is currently under review. And what is particularly interesting is that when we change the blending ratio, alpha is the blending ratio of hydrogen to ammonia, you see preferential diffusion and variance of the local equivalence ratio. So you see how the positive and negative curvature regions can be correlated with lower or higher local equivalence ratios. Finally, on the right, work in progress on 1D ammonia hydrogen air flame interaction with the wall. And there we have seen certain interesting anomalies near the wall. But as I said, this is work in progress, and we see the flame quenching, but there are certain interesting phenomena that you can also get out of these simulations. Finally, as you remember, I started my academic career with particle-laden jets and density-based solvers. And what else have we done? Where have we come from these considerations 10, 15 years ago? Here on the left, you see simulations on particle-laden jets in biomedical flow context. And this was work done during COVID-19. And in fact, I was honored to receive the Academy of Finland Award for science communication during COVID-19 on usage of CFD methods to illustrate how viruses are airborne and transmit in the air. And on the right, you see also work in progress to be submitted, combination of DLB foam with a density-based solver. And now we are currently looking at hydrogen detonations and also primary reference fuel detonations and the emerging physics out of this kind of systems is very different than we are used to in subsonic combustion. So as personal lessons learned from the past 15 years, I would say, first of all, DLB foam is a key enabler for computational feasibility. There are certainly benefits of the finite rate chemistry calculations. And it would have been difficult to address dual fuel problems without DLB foam. We provided the first numerical evidence of flame initiation timescale in dual fuel spray ignition problems, and premixed turbulent flame propagation in methane hydrogen and ammonia hydrogen blends is also possible to simulate with DLB foam. And finally, I would say that solving scientific problems is really a long road, and patience is needed. And I would say that multidisciplinary collaboration and teamwork is very essential in doing this kind of reactive flow studies. So thank you for your attention, and I wish you a nice continuation of the conference. Thank you.